Okay, we can move to the last speaker of the session, which is Thibault. I hope I pronounced it correctly. Are you here? Yes, some form. Okay, so Thibault will talk about.
I'm.
Yes, please go ahead.
Thibault Prunet. I'm a PhD student under the supervision of Nabil Absi, Valeria Borodin, and Diego Cattaruzza. And in this talk, I will speak about the storage location assignment problem in fast peak area. And I will present a novel formulation and decomposition method. So first, a bit of background on the literature in warehousing. So warehousing is a big part of supply chain, and it's a large key component of the operational performances of a logistic chain. So it has been quite studied in operation research. For the operational part, there are like two main topics that have been studied that are like storage, that is concerned with where to store the different items, and the order picking, mostly the routing of order picker to route the picker to retrieve all the item of an order. First, the storage that we will focus on in this talk. It's concerned by the decision of where to store the different items in the warehouse. What has been done in the literature is mostly class-based storage, because that's what is used in the industry as well, where the different items are separated into several classes, most of the time three classes, A, B, C, where 15% of the items represent 85% of the demand, and the different storage space we can see here from above are assigned to one class in different settings depending on the operational constraints. But there are also other methods that are used, but most of the time they are based on statistical data on the demand, like turnover of an item, its weight, its volume. Sometimes solution method also use like more sophisticated data, like the correlation between different items, about like how likely they are to be picked together. But in real life, one order includes several items that are picked all together. So with statistical data, it's a bit difficult to model accurately, like the picking routes and the distance to retrieve items. And that's the main point we will try to address in this talk. About picker routing, there are as well like several solution methods that have been proposed in the literature, some exact methods, some heuristic and meta-heuristic based method. But what is mostly used in the literature and in the industry as well are policy-based methods, where a simple set of rules are used to determine the picking route of a picker. So for example, the most simple one is like the S shape, where the picker starts at the depot, and an aisle is crossed completely if there is at least one item to retrieve in this aisle, and so on until the end. And at the end, the picker go back to the depot. A bit more sophisticated is the return method that we will use in the application cases for this talk, where for each aisle, the picker go to the farthest, to the farther item, to a farther location where there is an item to pick, and come back in the front aisle. Then you go to the next aisle, and again go to the farthest position and come back until the end, where it goes back to the depot. Then there are like more complicated methods where more and more optimization is done about the picker routing, and at the end, like the optimal routing method where the route with the minimum length is chosen. So what we will study in this talk is the storage location assignment problem. So it's to determine where to store a set of items in the warehouse. We will focus in the fast pick area. Indeed, in a warehouse, there are like several storage area. There is like the reserve area, like this one, where items are stored in bulk for long-term storage. It's really space efficient because the racks are quite high, but it's not really efficient for order preparation and order picking. Most of the time when a warehouse needs order picking, there is like a second storage area that is the fast pick area, where only a small quantity of each item is stored, and the order pickers are traveling with a trolley and getting all the items they need to for the preparation of one, sometimes several commands, several orders. So that's where we will focus on. So the objective is to minimize the total walking distance of order pickers to retrieve a set of order, like the demand is fully known in advance. There is a set of order, and in each order there is a list of items that need to be picked. This model, like a time horizon of a picking wave around 1 hour to a work day, in the industry, it's like where the demand is fully known. This problem with the full information on the demand has not been studied much in the literature, but we found one paper that studied it, a paper from Borodin and all, 2013, and they proved that the problem isn't hard in the strong sense, even in very simple cases. So what is the motivation to study this problem? First, there are like academic interest. The problem is interesting. It's highly structured, really combinatorial, so prone to decomposition methods. It hasn't been much studied despite being an interesting formulation of widely studied problem. Then it can enable to gain some insights on the rule-based heuristics used in the literature to know like how much performances and efficiency we lose by using partial data on the demand, and how much efficiency there is to gain by considering the full information. And it can be used in MIP-based heuristics, for example. From the practical interest, it's really suited to model the forward picking area. And we can gain some insights about the interaction between storage and routing that are really linked together, and the efficiency of one problem really affects the other. Then we present a very generic formulation that is suitable to a large panel of operational configurations. So first, I will present a generic compact formulation. So we have a set of SKU, single keeping units, that are the items, and a set of locations. And the main goal is to assign the SKU to the locations. So we have a set of C variables that are the assignment variables, and that are equal to 1 if one item is stored in location L and 0 otherwise. They are associated with this set of constraints here that are classical assignment constraints. One item should be stored in one location, and one location can store at maximum one item. Then there are the demand, the set of orders with for each order the set of items to retrieve. And for each order, there is like a set of X variables that are the routing variables. It's classical arc routing variables with here the classical set of routing constraints. So the X should form a valid tour. So we have like the subtour elimination constraints, the flow conservation constraints. Then there is the link constraint here for one order. The route servicing this order should pass by a location L if and only if there is an item to retrieve in this location. So that's the interesting constraint that link the two parts of the problem, the routing and the assignment. And the objective is to minimize the overall walking distance that is not expressed for now because it depends on the warehouse layout and the routing policy. So to give a bit matrix representation of the problem, we have here the assignment variable with the assignment constraints. For each order, we have a set of routing constraints. And then below, we have the set of link constraints. So we see that the matrix is highly structured and really prone to decomposition methods. So some comments about this formulation, it's really generic, it's independent from both the warehouse layout and routing policy. It's highly structured and an incumbent is easily available. You just need to give an assignment plan and then the other variables follow to give a feasible solution. But it has some drawbacks. It's intractable to use like a distance matrix in a general case that can model every operational configuration. Between the different routing policies, you need to adapt a bit the model. So it's not easy to get like one general MIP that concern like all possibilities. And the linear relaxation is really poor, like around 85% gap. So we need to improve the dual born for this problem. We will propose a Danzig-Wolf formulation. So we will convexify all the variables and constraints concerned by the routing variable X. And we will replace them by a set of routes. So for each order, we have all the set of feasible routes. That is like a route is feasible if first it's a valid tour with no sub-tour or anything. And then it has the good number of stops. If one order has 2 items, then the route servicing it should have 2 stops, no more, no less. So if route R is chosen, then the variable rho OR is equal to 1, 0 otherwise, and is associated with the cost. So the objective is to minimize the sum of the cost of the chosen routes. So this time it's linear. Here we have for each order, there is like at least one route that has to be chosen in the solution. And the link constraint remains the same where for one order and one location, if the one item of this order is located in location L, then the chosen route should stop in location L. Just to have a small look at the dual problem that decompose into several sub-problems. We have like for one order, the reduced cost, we'll have like an offset here that is a constant, and we add one term for each visited location. That is like a price that is added to the reduced cost. So some remarks. It's a really general master problem, still independent from operational considerations. So it decomposes into several sub-problems, one for each order. So that's quite nice. One interesting thing is that the assignment variables, C, that are the main decision variables that we need to determine, do not appear in the objective function. So that's also quite interesting. And the relaxation is way better. The pricing problem is where like all the information about the warehouse layout and routing policies are taken into account. And it's mostly a routing problem with price collection with a defined number of stops. Like if one order has 2 items, the route should have 2 stops. So some preliminary results. We run some tests on random instances that are like size of instances we hope to solve with an effective exact method and the return policy. So we see that here there is the optimal value, and the linear relaxation is really poor for an optimal value of 2060. The relaxation is 35, so 87% gap. That's really a lot. And with the column generation, the mean gap is 24. That is still quite big, but way better than with the linear relaxation. So some perspective, what we are trying to do now is to strengthen further the dual bound by adding valid inequalities. We have found several of them and are currently working on adding them to the column generation. And then we will try to speed up the process and integrate the column generation in a competitive bunch and price, maybe uncut solution method. Thank you for watching, and do you have any question?
So, do you have any questions? From Vienna?
No, not at the moment.
Okay, so I do have one. So what's the size of the instances that you are currently able to solve with this approach?
It's quite small instances, on between 20 and 50 items stored in the warehouse, and with we are trying to solve small instances with 20 orders and around 3 picks per orders, and larger instances where we have like 50 orders.
Okay. And what are you used? So I understood that you implemented this dancing wolf decomposition. So which software are you using it for that? So is it a home implemented scheme, or do you use some general purpose frameworks like, I don't know, Skip, GCG or something like that?
No, we are implementing everything.
Okay. Okay, so if there are no further questions, we are really sharply on time. I would like to thank all the speakers of the session again. And I would say that we can enjoy our coffee break then.